that turns out to realize something that's actually very, in many ways, are analogous to this stiffer liquid we're talking about. In fact, the stiffer liquid, you can view that as kind of the generalization of that story. And that was first theoretically understood back in the, I think, 1920s. That's almost 100 years.
Yeah.
Very soon after quantum mechanics was established. But it was decades later only that people realized that in the lab, and all the measurement signatures matched perfectly well with the theoretical prediction. And that was a pretty exotic state. It's not an ordinary, not a classical magnet, right? Classical magnet, the magnetic moment just pointing in some direction and that's it.
Yeah.
This one is not. This one, the magnetic moments keeps fluctuating, but in a non-trivial pattern that you measure correlation function, there's some non-trivial, like power law decay of things. So, in field theory language, it's a non-trivial CFT, it's a conformal field theory. So that's an exotic matter that people have found. And a lot of the, past effort since the 70s, is to find higher dimensional analog of that. Because for a little while, people think, yeah, that's a special thing about one dimension. There are many things special about one dimension. Right? I mean, as you can imagine, in one dimension, the effect of interaction will be stronger because if you have two particles moving with different speed, they will meet at some point, so they will have to collide. That's not true for higher dimension. So, but the lesson I think people accumulated over the past several decades, at least theoretically, is that those things are not that special in one dimension. It's just that it's in one dimension, that kind of thing is easier to happen. It's easier for that kind of thing to happen. But in higher dimension, you do have to work a little bit harder to find the right material, to find the right microscopic system. But a lot of analogous low energy theory, meaning like analogous basis of matter, do exist.
Yeah. So you can actually go from find something in one dimension that's interesting that we don't normally see in the world, but then if you extrapolate it later on, it can be maybe found in 3 dimensions. Or...
Yeah. For example, that's one of the things. Right? How do you upgrade your understanding from 1D to 2D and 3D, which turned out to be surprisingly challenging. You can't just naively stack them together. You don't understand how to do that. So,
But could it lead, do you think it could lead to something like the stiffer liquids? I mean, could it lead to a new material or a new...
I mean, we think it's somewhere there, right? It's typically it's just that it could well be that some material are already described by this kind of theory.
Okay.
But you just need to measure the right signature.
I see. Okay.
Right. I think one example, in terms when we talk about history of physics, is that the topological insulator, which you probably have heard of, that the theory was proposed in around 2008 or 2006. I don't remember. But the material that the quote unquote first material realization of that topological insulator, that's a well-known material for decades. It's actually even being used in things like water heater and so on. So it's not a super exotic material. It's just people never bother to measure the right signal to see that it's a non-trivial thing, right? So the difference. So on that regard, it could well be a similar situation. The difference is that for topological insulators, because that theory was regarding non-interacting or weakly interacting electrons, so there are much better numerical tools to calculate detailed